March 17, 2026, 02:40 a.m., Strait of Hormuz. The sea is black, but not silent. Thermal layers ripple across the water as a 45,000-ton amphibious assault ship moves at a controlled 18 knots, its wake stretching like a scar across one of the most militarized choke points on Earth. USS Tripoli is not supposed to be here. Not this close. Not at this time. The Strait of Hormuz narrows to just 21 nautical miles at its tightest point. Within that corridor, commercial shipping lanes compress into two channels, each barely 2 miles wide. Everything inside that space is predictable, trackable, targetable. And tonight, that predictability becomes a liability. Satellite constellations have already mapped the vessel's vector. Coastal radar installations along Iran's southern shoreline are cycling every 12 seconds. Passive listening stations are triangulating emissions, and somewhere inland, mobile missile batteries are calculating firing solutions. The paradox is simple. Why would the United States Navy deliberately move a high-value amphibious assault ship into a confined kill zone where reaction time is measured in seconds, not minutes? Because sometimes the safest place is where the system performs best, but that only works if the system is perfect, and in the Strait of Hormuz, nothing ever is. So, the question is not why USS Tripoli entered the kill zone. The real question is, what invisible system made this movement survivable? The Strait of Hormuz is not just geography. It is a mathematical problem. At its narrowest operational corridor, the distance between hostile shorelines and the center of the shipping lane is roughly 10 to 12 nautical miles. That distance defines everything. Coastal anti-ship missile traveling at Mach 2, approximately 680 meters per second, can cover that distance in under 30 seconds. Mach 3 reduces that window to less than 20 seconds. That is not response time, that is decision time. Because detection, classification, and engagement must happen before the missile even crosses the midpoint. Now consider radar physics. The curvature of the Earth limits surface-based radar detection. A ship-mounted radar positioned 20 meters above sea level has a horizon of roughly 16 nautical miles. Low-flying, sea-skimming missiles can remain below that horizon until the final seconds of their approach, which means the ship might not even see the threat until it is already inside engagement range. Add clutter. The strait is one of the busiest maritime routes in the world. Dozens of commercial vessels, varying speeds, overlapping radar signatures. Each one introduces noise. Each one complicates identification. Now layer electronic warfare, signal jamming, decoys, false targets. The system is no longer tracking a single missile. It is solving a dynamic equation with incomplete data. And then there is geometry. USS Tripoli is not a destroyer. It is 257 meters long. Its radar cross-section is significantly larger. Its maneuverability is lower. Turning radius increases with displacement, meaning evasive action is slower, wider, and more predictable. In confined waters, that limitation becomes critical. There is no open ocean to maneuver into, no space to create uncertainty. Every movement is constrained by shipping lanes, territorial boundaries, and shallow seabed topography. This is what makes the strait a kill zone, not because it is narrow, but because it compresses time, space, and information into a single, unforgiving equation. And in that equation, the defender is always at a disadvantage, unless the defender changes the equation itself. What made this operation possible was not armor, not speed, not even firepower. It was a system that extends perception beyond the physical limits of the ship. USS Tripoli does not rely on its own radar as its primary sensor. That would be too slow, too limited. Instead, it becomes a node in a distributed sensing network. Hundreds of miles away, airborne early warning aircraft operate at altitudes above 30,000 feet. From that height, radar horizon extends beyond 200 nautical miles. That changes everything, because Now, detection does not begin at 16 nautical miles. It begins at 200. A missile launch is no longer a surprise. It becomes an event with timeline. Detection, classification, prediction. Each stage buys seconds, and in modern naval warfare, seconds are the most valuable resource. Data from these airborne platforms is transmitted through secure data links. Link 16, Cooperative Engagement Capability Systems, feeding directly into the ship's Combat Information Center. But this is not just data sharing. It is data fusion. Multiple sensors, multiple perspectives, combined into a single coherent track. The system does not just show where a threat is, it predicts where it will be. And more importantly, when. This transforms defense from reactive to preemptive. Instead of waiting for a missile to appear over the radar horizon, the system calculates its trajectory long before it becomes visible. Engagement decisions can be made earlier. Interceptors can be launched sooner. Geometry shifts in favor of the defender, but sensing alone is not enough, because knowing a missile is coming does not stop it. The system must also solve the interception problem, and that is where timing becomes critical. A standard surface-to-air interceptor travels at speeds exceeding Mach 3, but it still requires guidance. It must be launched at the correct moment, along the correct vector, with continuous updates. Too early, and it wastes energy. Too late, and it misses the window entirely. The solution is not human reaction, it is automation. Algorithms process incoming data, calculate intercept solutions, and present options to operators within seconds, sometimes faster, because in a 20-second engagement window, hesitation is failure. USS Tripoli itself may not carry the most advanced interceptor systems, but it does not need to, because it is not alone. Destroyers operating in layered positions provide outer defense. Cruisers extend radar coverage. Submarines monitor subsurface threats. And airborne assets complete the vertical dimension. This is not a ship. It is a system. A distributed, synchronized network designed to compress reaction time and expand awareness. And in the Strait of Hormuz, that system is the only reason survival is possible. But systems are never uncontested, and as USS Tripoli moves deeper into the corridor, the equation begins to change again. The system was designed for clarity. The strait does not allow it. At 03:12 a.m., the first disruption appears, not as a missile but as ambiguity. 3 fast-moving surface contacts emerge from the northern coastline. Their radar signatures are inconsistent. Civilian hull profiles, but acceleration curves that exceed standard commercial limits. Speed, 45 knots. Vector, converging. Distance, 18 nautical miles and closing. Individually, they are not a threat. Collectively, they complicate the equation, because, in confined waters, classification is not binary. A small craft can be a fishing vessel, or a missile platform, or a decoy, and the system must decide before intent becomes impact. At the same time, electromagnetic noise begins to rise. Broad spectrum. Interference pulses across multiple frequencies. Not enough to blind sensors, but enough to degrade clarity. Signal-to-noise ratios drop. Tracking confidence decreases. Now the system is no longer operating with certainty. It is operating with probability. And probability introduces delay. Every additional second spent verifying a contact is a second lost in the engagement window. This is how modern denial systems work. They do not need to destroy sensors. They only need to slow them down, because delay in a compressed battle space is equivalent to vulnerability. Then comes the second layer. At 03:14 a.m., a high-altitude radar platform detects a thermal bloom 120 kilometers inland. Infrared signature spike, rapid acceleration. Within 2 seconds, the system classifies it. ballistic profile, short-range anti-ship missile, speed, accelerating past Mach 3 trajectory, descending, estimated time to terminal phase. Under 90 seconds. This changes the geometry entirely. Sea-skimming missiles compress horizontal time, ballistic missiles compress vertical time, and the defense system must solve both simultaneously because the interception problem is now multi-dimensional. One threat approaches at low altitude, masked by sea clutter. The other descends from above, faster, with a steeper angle. Different sensors, different interceptors, different timing solutions. But one shared constraint. Time. USS Tripoli is no longer just navigating a choke point. It is operating inside a layered threat envelope designed to overload decision-making capacity, and the system begins to feel the strain. Inside the Combat Information Center, the architecture reveals its true purpose. Every sensor feed is not treated equally. They are weighted, prioritized, filtered. The system assigns confidence levels to each track based on origin, consistency, and correlation with other sensors. The fast boats are now classified as uncertain hostile. Not enough evidence to engage, too much risk to ignore. A destroyer positioned 25 nautical miles ahead adjusts course slightly, placing itself between the contacts and USS Tripoli. This is geometry as defense, not interception. Positioning. Because, by shifting angles, the destroyer expands its radar coverage and creates a new engagement envelope. Now, if those vessels launch anything, detection time increases by critical seconds. This is how layered defense works, not as a wall, but as a series of overlapping fields, each one buying time for the next. Meanwhile, the ballistic track continues to evolve. Its mid-course phase is predictable, but terminal guidance is not. Modern. Anti-ship ballistic missiles adjust trajectory during descent, using onboard sensors to refine targeting, which means the intercept solution cannot be static. It must adapt in real time. A cruiser further south initiates engagement, interceptor launch, velocity. Mach 4+, climb angle optimized for mid-course intercept. But here, physics introduces another constraint. Interception is not just about speed, it is about geometry. The interceptor must meet the target at a precise point in space. Too far, and it cannot reach. Too close, and reaction time collapses. The system calculates this intersection continuously, updating as new data arrives. Milliseconds matter, because at these speeds, a 1-second error translates to hundreds of meters. And hundreds of meters is the difference between interception and failure. Then the system encounters its most dangerous condition: conflict between data. At 03:15 a.m., one sensor reports a deviation in the ballistic trajectory. Another does not. The discrepancy is small, less than 2 degrees, but at high velocity, that deviation compounds rapidly. The system must decide which data to trust. This is where human operators still matter, not for reaction speed but for judgment. Algorithms can process data. They cannot interpret uncertainty with context. An operator reviews the sensor sources, evaluates historical reliability, cross-references with environmental conditions, wind patterns, thermal distortion, signal interference, and makes a decision. The trajectory is adjusted. Interceptor guidance updates. This entire process takes less than 5 seconds, but those 5 seconds determine whether the engagement succeeds. If you appreciate the engineering behind modern military power, type proud in the comments. At 03:16 a.m., the engagement reaches terminal phase. The ballistic missile descends at extreme velocity. The interceptor climbs to meet it. Closing speed exceeds Mach 7. There is no explosion yet, only mathematics. Two objects moving through three-dimensional space, guided by continuous streams of data, attempting to occupy the same coordinates at the same time. And then, contact, not a visible detonation, but a brief spike in infrared kinetic. Interception. Energy transferred through impact, The incoming threat fragments at altitude. Debris disperses. Trajectory broken. But the system does not pause, because the horizontal threat remains. The fast-moving surface contacts have closed to within. 12 nautical miles, and now new signatures appear. Heat sources. Mounted aligned missile rails. The ambiguity is gone. The equation simplifies, but the time window collapses. Because at this range, engagement is no longer strategic. It is immediate. And USS Tripoli is now inside the final layer of the kill zone, where systems are tested not by design, but by execution. The transition from detection to engagement is no longer measured in minutes. It is measured in seconds. At 03:17 a.m., the system shifts from layered defense to terminal response. The fast attack craft accelerate again, now exceeding 50 knots. Their vectors tighten, no longer probing, but committing. Fossilate between them reduces, forming a coordinated attack geometry designed to saturate defenses from multiple angles. Distance: 9 nautical miles. Time to potential launch: under 60 seconds. But unlike the ballistic threat, this engagement will not be solved at altitude. It will be solved at the surface, and at the surface, clutter becomes the battlefield. Sea state reflections, thermal interference, civilian vessel proximity, all variables that distort targeting solutions. Yet the system adapts. A forward-deployed destroyer activates its fire control radar, switching from wide-area surveillance to precision tracking. The beam narrows. Resolution increases. Each fast craft is now an isolated track, no longer part of background noise. Simultaneously, airborne assets adjust their orbit. Angle changes. Sensor overlap increases. This creates redundancy, because in high-noise environments, a single sensor can be deceived. Multiple synchronized sensors cannot. The system begins cross-verification in real time. Position, velocity, acceleration, all matched across independent sources. Confidence level rises. Authorization follows. At 03:18 a.m., the first defensive action is executed, not from USS Tripoli, but from the perimeter. A guided missile destroyer launches surface-to-surface precision munitions. Unlike long-range interceptors, these are optimized for short flight times and low-altitude trajectories. Speed: subsonic to supersonic transition. Flight path: sea skimming. Purpose: minimize reaction time for the target. Because the fastest way to defend is not to intercept the missile, it is to remove the launcher. Within seconds, the first strike connects. One fast craft disappears from the system, not visually, but digitally. Its track vanishes. Velocity drops to 0. The equation reduces. 2. Targets remain, but they are no longer synchronized. The loss disrupts their attack geometry. Spacing increases, coordination degrades, and in modern warfare, disruption is often more valuable than destruction. The second craft attempts to compensate. It alters course slightly, likely recalculating its firing solution. But this maneuver introduces a new problem: predictability, because any